Hey there, this is a lecture for section 8.4, vectors. All right, let's start with a definition. A vector, it's an object that has both length and direction, right? So if we were to draw a vector, it might look like this, okay? We indicate them with an arrow when we're drawing them. The length of that vector might be 5. And the direction, as we can see, I'm going to say that's maybe, we'll say 45 degrees north of east. Is one way to describe the direction of that. North of east, of course, that's if I'm thinking about the traditional compass directions, where up is north, down is south, left is west, and right is east. Okay. Another way to measure the direction is with an angle in standard position. I might say there's an angle there, theta, that's 45 degrees. All right. So different ways that we can represent vectors, right? We could say A, B, where the starting point of the vector is A and the ending point of the vector is B with an arrow on top. We might also just indicate it with a letter in bold, like U. But more commonly, in the way I'll be doing it, is with the letter, whatever we want to call that vector, say it's U with an arrow on top. All right, so let's take a look at drawing vectors. If we want to draw a vector, the vector v that travels from the origin to the point 2, -3. Let's see, the point 2, -3 is right there. So that vector is going to look like that, right? If it starts from the origin. So there's vector v. Vector u doesn't start at the origin, but it travels from the point with the coordinates -5, 4 to the point with the coordinates 2, 1. Right? So where's -5, 4? This one's going to start here. It's going to travel to 2, 1. It's going to end there. So there's our vector u. All right, we can add vectors. To add them geometrically, we just position the second vector at the end of the first vector. Right? So if we have vectors u and v as drawn here, here's vector u, here's vector v. To add vectors u plus v, I will position vector v at the end of u, right? So let's see if I can draw that. It's going to be maybe like that. There's vector v. I just kind of moved it there at the end of u. Now the resulting vector would be the sum, right? So we start at the original starting point and connect to where we end up. The black vector that I just draw would be u plus v. Okay, we can also scale vectors geometrically, right? And by multiplying that vector by a constant, right? And then we could subtract vectors too. When we scale them with a negative constant, we're simply changing the direction of that vector, right? That's like multiplying. So if we've got this little vector here, u, looks like this. 3u, it's just going to be that vector with that same direction. Here, we'll draw it here. It's going to have that same direction, but the magnitude or length of that vector is going to be multiplied by 3. So it might look something like that. All right. Negative u, it's going to have the same length as u, but in opposite direction. So the vector negative u might look like that. It's supposed to have the same length. It's an opposite, but it goes in the opposite direction. All right, -4u, well, that one, we're going to multiply that vector's length by 4, but it's also going to go in the opposite direction, right? So that one's going to look something, not a very straight line, is it? Let's try that again. Let's see, if that's 3, we'll say this is 4. It's going to go in the opposite direction. Okay, so when we subtract vectors, we're really just adding a vector in the opposite direction, right? So if I've got this vector u and this vector v, and I want to subtract v from u, right? If I was adding v from u, I would put it here like that and then draw the connection. But that's not what I want to do. I want to subtract it. So it's going to go the opposite way. It's going to go the opposite direction. It's like I'm adding negative v, right? So go like that, and the result, so that'd be negative v right there, and the resulting vector would be this guy here, u minus v. All right, so I mentioned magnitude. Magnitude is the length of the vector. Okay, we represent the length of the vector either as the vector name enclosed in double bars or single bars, or the vector name enclosed in double bars. All right. One more term is the unit vector. The unit vector has a length of 1. All right. So we can represent vectors in their component form, which is a much easier way to deal with them mathematically, right? Geometrically, you can see I just kind of sketch in to try and illustrate the concept, but it's not very precise, right? Not without some tools to make it precise. When we want to deal with vectors mathematically, it's better to put them in component form, right? So there's two ways we could write them in component form. First way is just to specify the horizontal and vertical components of that vector enclosed in these little like stretched out arrows. It's not a parenthesis, it's not a square bracket, it's just like a little stretched out arrow. That indicates that's a vector, all right? And the horizontal component, if you drew the vector, look, here's vector u, the horizontal component would be the x, or the horizontal leg of the triangle if you dropped a perpendicular and made a right triangle, right? The vertical component would be the vertical leg of that triangle. All right. So the magnitude of this vector can be found if I consider a triangle. I could use the Pythagorean theorem, right? If I knew the components, right? Or if I'm thinking about polar form, the magnitude would be the radius, or r. All right, so we mentioned that there was a unit vector. There's another way that we can represent vectors in their component form, right? And that's as multiples of the unit vectors, right? So the unit vector, the horizontal unit vector, has a horizontal component of 1 and a vertical component of 0, right? So if we drew it, it would look like that. That's vector I. Has a length of 1. And then the j, vector j, unit vector, the vertical unit vector, if I drew it, it would look like that. It has a 0 for the horizontal component and a 1 for the vertical component, right? So this vector that has a horizontal component of 3 and a vertical component of -4 could also be written as this vector u equals 3 times the unit vector I minus 4 times the unit vector j, kind of wrapped around, so I'll put it up there. Okay, it's just different notation for saying the same thing. The unit vector 3, -4 could also be written as 3i minus 4j, and that's the same exact vector, just different ways of specifying it. All right, so let's look at some examples. If we have a vector of magnitude 5 points in a direction 75 degrees counterclockwise from the positive x-axis, find the components of this vector, right? We'll start with a little diagram and draw it. Okay, 75 degrees from the horizontal is about like that, okay? If it's 5 points, so we're measuring the units, we're measuring this vector in as 5, okay? Now to find the components of that vector isn't going to be that challenging. If I drop a perpendicular and make a right triangle, I could use, well, there's a number of ways that I could find the vertical and horizontal components. Probably the easiest thing is to use these definitions, these polar definitions that we've been working with, that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. All right, so let's find the components. The x component, r, that's 5, times the cosine of theta. Theta is 75 degrees. Now let's see what that value is. 5 cosine 75, and it's 1.2941. I am still in degree mode. Okay, 1.2941. All right, let's find the vertical component then. That's going to be 5 times the sine of 75 degrees. Okay, 5 times the sine of 75 degrees, and that's 4.8. Go away. 4.8 4.8296. Right? So they can write this vector, we'll call him vector V. If I wrote it in component form, it would look like this, 1.2941 for the horizontal component, 4.8296 for the vertical component. The legs of this triangle that we made here, the horizontal leg length is 1.2941. The vertical leg length is 4.8296. Okay. I could also write this vector in terms of unit vectors. Another way to specify this, I could also say this is 1.2941i plus 4.8296j. Okay, same thing. Just specified two different ways. All right, let's look at the next example. We want to find the component's magnitude and angle of the vector that travels from the origin to the point with the coordinates 3, 5. Okay, well, again, let's sketch that. 1, 2, 3, up 5. So there's the point with the coordinates 3, 5. There's my vector. It's traveling from the origin to that point. So there's my direction. It is forming some angle here. And if I drop a perpendicular here, make a right triangle, okay, the horizontal leg of this triangle is going to be 3, and the vertical leg of this triangle is going to be 5. So to find the magnitude, we'll call this vector u. So to find the magnitude of vector u, right, that's finding the length of that hypotenuse, right? Well, we know this Pythagorean theorem says that, wrong thing, sorry about that. We know the Pythagorean theorem says leg squared plus leg squared is hypotenuse squared, or from our polar relationships, the radius r squared is x squared plus y squared, right? So the square root of r then is the square root of x squared plus y squared, right? So I could then say the magnitude of this vector u here, let's label him, is going to be the square root of the horizontal component squared, that's 3 squared, plus the vertical component squared, that's 5 squared. Or that's the square root of 9 plus 25, square root of 34. All right, so there's the magnitude. Magnitude of that vector. What else? Oh, the components. Well, we've got the components there, 3 and 5. Let's write it in component form. Component form, I could say this vector is 3, 5, or if I did it in terms of unit vectors, it would be 3i plus 5j. Okay, last thing I need to know is this angle, which tells us about the direction of the vector, because the vector must have magnitude and direction. All right, well, that angle isn't that hard to find. If we could use tangent, cosine, sine, it doesn't really matter. If I use the tangent, I could say that the tangent of theta, that's opposite over adjacent, right? It's 5/3, or if I take the inverse tangent of both sides, theta is going to be the inverse tangent of 5/3. Let's see what that is. Inverse tangent, 5 divided by 3. And it looks like it's 59 degrees. Okay. So I would say that vector u has a magnitude of the square root of 34 in the direction of 59 degrees. I could say north of east if I wanted to, or I could say at an angle of 59 degrees in standard position. Those would all be correct ways to describe that. All right, so when vectors are in their component form, they're easier to deal with when we want to add, subtract, or scale them, right? If we add the vectors, we're just going to add the horizontal components and add the vertical components, right? To subtract them, we want to subtract the horizontal components and subtract the vertical components, right? To scale it, we just multiply that scale factor. We multiply both the horizontal and the vertical component by that scale factor. All right, so let's look at some examples here. if we have a vector u that has the horizontal component of -3 and the vertical component of 4, all right, and vector v has the components -2, 1, compute vector u plus vector v, right? We're just going to add these horizontal components first. So that'd be -2 plus a -2, I'm sorry, -3 plus a -2 or minus another 2, right? And then 4 plus 1, or -5, +5. Okay? To subtract them, just subtract the horizontal components and then the vertical components, right? So this is u minus v, so it's going to be the horizontal component of -3 minus the horizontal component of v, that's -2, and then the horizontal component, or I'm sorry, the vertical component of u, 4, minus the vertical component of v, 1, right? Which is -3 plus 2, or -1, and then 4 minus 1, 3. Right? Here we're going to do a couple of things. We're going to compute 2u minus 3v. Right? So I would say scale it first and then subtract them. Okay? So I want to multiply the components of unit u by 2. Right? Unit u. Multiply the components of vector u by 2. Right? So -3 times 2 is -6. Right? And and then 4 times 2 is 8. And I want to subtract 3b from that. So 3 times -2 is -6. Okay? And then 3 times 1 is just 3. Now I'll subtract those scaled vectors. -6 minus a -6, that's -6 plus 6, or 0. And then 8 minus 3 is 5. Right? Okay, let's close out with a couple of applications. Why do we learn all this stuff? Let's see how this can help us. All right, this first application is a real doozy. There's a lot going on here. We have a person. They start walking from home. All right, let's see. We're going to need to sketch this out. So if they start walking from home, we'll say that's right there. All right, and they're going to walk 4 miles east to begin with. Okay, directly east. So there we'll say that's a vector of length 4 in the direction east. And again, we're using north, east, south, and west as our directions. Okay, so that's the first part. Then they go 2 miles southeast. Okay, so they're going to, at a 45-degree angle here, southeast, they're going to go 2 more miles. All right, then 5 miles south. Okay, directly south would be down, and that's 5. All right. At 4 miles southwest, okay, probably should have made that, let me try to make it a little bit to scale and make that one a little bit bigger. Okay, now 4 miles, that's going to be at a 45-degree angle again, southwest, and then lastly, 2 miles east. Okay, that's where they end up. So that's kind of a sketch of the path they're taking. How far have they walked? All right, so you want to add the magnitudes of all these vectors to find out how far they walked. Right? Well, let's label them. Let's see. Let's call the first one vector 1, vector sub 2, then vector sub 3, vector sub 4, and vector v sub 5. There, with those 5 vectors. Okay, so we're going to add those up to see how far they walked. So we're going to need to put them in their component forms. All right, so vector 1, the horizontal component is 4. There's no vertical component, so that would be 0. All right, vector 2, oh, well, I got to find my horizontal and vertical components there, don't I? So make a little triangle. Can I do it here? I drop a perpendicular. Yeah, I don't. Let's do it this way. I'm going to break that out. triangle is going to go over here separately. Okay, I want to drop the perpendicular this way. Okay, so this is 45 degrees here. Actually, let's try that one more time, even a little bit bigger. So there's some room to write. Okay, we're dropping that perpendicular. This is the vector. It has a magnitude of 2. Okay, and this angle, since they're walking southeast, we can assume that the angle is 45 degrees. Both of these angles would be actually. All right. So to find the vertical and horizontal components, right? There's a number of things I could do. Probably the easiest thing to do is use x. X is the cosine of 45 degrees, and y is the sine of 45 degrees. And it doesn't matter which angle I'm using here at all, right? Let's see, if I use this angle, it doesn't matter. They're going to be the same exact value. So what is the cosine of 45 and the sine of 45? I could grab that from the unit circle, couldn't I? That's a known value. Let's see, do I have a unit circle? There's one. 45 degrees, that's right here, pi over 4. Look, the x and the y coordinates are both square root 2 over 2. So the sine and the cosine are both square root 2 over 2. So there's the cosine, there's the sine. Okay. To find, x equals, I forgot the radius here, so let's put that in there. In this definition, x equals r cosine square root 2 over, or square root of 45 degrees. Start again. X equals r times the cosine of 45 degrees. So x here is going to be r. That's 2 times the square root of 2 over 2, which of course is just the square root of 2, and the sign will be the same. So there's our horizontal and vertical components for vector 2. Now, we've got some positive and negative situations going. Look, the horizontal component, that's what we're trying to, is positive, right? So that's going to be square root of 2. But the vertical component, we're moving down, so that's going to be negative square root 2 over 2. All right. Another way to think about this is we're over here in quadrant 4. If I were to place this, on an axis like that, I'm over here in quadrant 4, where x's are positive and y's are negative. All right, so vector 3, it has no horizontal component, so that'll be 0, but the vertical component is 5, but we're going down 5, right? So that's 5 in the negative direction. All right. Vector 4, let's see, if I were to imagine that, right, in a circle, I'd be over here in quadrant 3. It's going southwest, so it's making a 45-degree angle. Okay, so I know that the cosine, or that x and y are going to be square root 2 again. Right? It's really the same triangle, just moved around a little bit, right? Reoriented. The x coordinate here is negative, the y coordinate is negative as well, because we're over here in quadrant 3, right? So that's going to be negative square root 2 over 2, negative square root 2 over 2. And then, what do I have last? One more, vector 5. The horizontal component here is negative 1. All right, there's no vertical component, so that's 0. All right, so we've broken these vectors down into component form so we can work with them. Now, what are we answering again? First of all, just how far have they walked? Okay, so the total distance walked, we just want to add the magnitudes of the vectors. All right, so let's see, we'll do that maybe in red. How far have they walked? Add magnitudes. So that's just going to be 4 plus 2 plus 5 plus 4 plus 2, or what is that, 6, 11, and 6. They've walked 17 miles. All right. So that's how far. Now the next question says, if they walked straight home, how far would they have to walk? All right. So if they walked straight home, let's do that one in, say, purple. They'd be going like this, right? I may not have drawn that exactly right to scale, but you know, it's something like that. All right. Call this guy vector 6. All right. So what do we want to find here? To determine how far they would have to walk, we want to find the magnitude of vector 6, don't we? Yeah. So to find the magnitude of vector 6, I'm going to need to think about that as a triangle. Right? It would be the R, or it would be the hypotenuse of a triangle, and it's going to have both a horizontal and a vertical component. So let's erase this. There's no more room. Let's see if we can sketch that triangle here. Let's see, if we drop a perpendicular like this. Okay, there's one triangle that we could work with. All right. So let me just blow it up or redraw it again here. Here's the triangle that we're going to work with. All right, here's our triangle. So we, the magnitude of that vector is going to be the hypotenuse, and then the components are going to be the vertical and horizontal. So how do we find that, right? Well, we're going to have to add, all these other 5 vectors, right? Add them up. Okay, so let's go ahead and do that. Let's go ahead and add them up. We'll sum them. V sub 6. All right. So if we add the horizontal components, it's going to be 4 plus square root of 2. Let me just write it all. 4 plus square root of 2. That's just a 0. Then minus square root of 2, and then minus 1. There's the horizontals. Now we'll add up the verticals. That's going to be 0 minus square root of 2 minus 5 minus the square root of 2, and then there's a 0 plus or minus that 0. All right, let's simplify that. So we've got a 4 minus 1, or a 3. The square root of 2's, they add out. So the horizontal component is 3. I've done that properly. And the vertical component then is going to be negative 5 minus 2 square roots of 2. All right, so there we go. So the horizontal component here would be 3. The vertical component is negative 5 minus 2 square roots of 2. All right, let's see if we can find that magnitude of vector 6. I don't know where that came from. So the magnitude of vector 6 is what we're looking for. It's going to be the square root of oh my, okay, 3 squared plus negative 5 minus 2 square roots of 2 squared. All right, because remember, that's magnitude squared is leg squared plus leg squared. So the magnitude itself would be the square root of leg squared plus leg squared. All right, and let's see if we can find out what that value is. Okay. So we want the square root of 3 squared. That's 9. And then plus a negative. So we'll just say minus, not plus, minus, I don't know for my exact values, 5 plus, I'm pulling the negative out, square root 2 of 2 squared. Okay. I'm sorry, that's 2 square roots of 2 squared. Let's put parentheses, 2 square roots of 2. Get out of there, close that, and square it. All right, yep, that's right. Okay, so equal. I didn't do something right. Let's go see. What did I type in wrong? The square root of 9. All right, let's say 9 plus negative. Let's see. Let's change. Oh, I know. We'll say, like I wrote it, 9 plus. Let's insert a negative in there. Negative 5 minus. There. Non-real answer. So it's 9, 3 squared plus. Oh, so it's got to be a squared. Okay, got it. It's late in the day. The square needs to come outside of that parenthesis. I didn't type this in right. Let's try it again. Because I want to square that whole thing. Now let me just insert a parenthesis. Okay. It'll probably not complain about. Okay. I got an extra parenthesis under that radical there. Let me get rid of him. I may just have to type this whole thing. Okay, there we go. 2 square roots of 2. I need a parenthesis outside there. All right, so let's try it here. Still didn't get that typed in properly. All right, I'm going to get it eventually. I'm going to retype the whole thing. It'll be easier. Okay. Is that right now? Okay. 3 squared, that's 9. Plus, and then we want negative 5 minus 2 square roots of 2. And square that whole thing. Okay, finally. Sometimes the large points get in the calculator, isn't it? All right, so there we have it. The magnitude of that vector is 8.3836. All right, so now what? Let's see. So that's how far this person would have to walk going right straight home. 8.3836 miles. Okay. Now we have one more question to answer. In what direction would they need to be walking here? All right, well, if this is drawn right, they're going to need to be walking west of north, right? So how would we specify that direction? I may have to change my triangle up a little bit, right? Let's put north in there right here. Let's put a little, okay, that's going to be north, all right? So the angle that I'm looking for is this little guy here, right? Well, I'm just reorienting my triangle. The horizontal component is still 3, and the vertical component is still that, negative 5 minus 2 squared roots of 2, right? So I could use inverse tangent here to find that angle measure. That's probably the easiest thing to do. All right, so my angle then, I can say that the tangent of theta, my little angle there, which is going to give me that direction, it's going to be opposite over adjacent sides. So 3 over negative 5 minus 2 square roots of 2, right? Take the inverse tangent of both sides. So then theta is going to be the inverse tangent of 3 over negative 5 minus 2 square roots of 2. Now let's see what that is. Inverse tangent, 3 divided by, in parentheses, negative 5 minus 2 square roots of 2. Now, did I get that typed in properly this time? That looks good. And I see it's going to be negative 20.9677 degrees. That's not exactly what I want, is it? So let's see, we'll have to reorient. Let's see, 9678, sorry. Just tapping there, it blew up a little. So, whoa! Don't know what I just did there. Okay, so it's given me the negative angle because tangent is restricted to quadrants 1 and 4. So I need to know what the angle that it gave me, right? The angle that it gave me was more this one, right? But I need this one over here, don't I? So that's going to be right crossing there. So it's the same thing, really. So we've got 20.9678 degrees west of north, right? Let's try that. Oh, my goodness. The computer is not a happy one right now. All right. So the answer we want to say is 20. It's almost 21 degrees, right? 9678 degrees, and we're going west of north. All right. Woo, that was a lot of ordeal, wasn't it? Kind of a good process of going over all the details, though. A little bit. That's about right. Okay, so one more example before we close out the lecture. In this one, we have an airplane. They're heading north at an airspeed of 600 kilometers per hour. Okay, but there's a wind blowing from the southwest at 80 kilometers per hour. All right, so we can represent these speeds as vectors, right? So if we're heading north at 600 kilometers per hour, we can say there's a vector that's 600 kilometers per hour. And then, but the wind now is southwest. All right, it's blowing from the southwest. So it would be going this direction from the southwest at 80 kilometers per hour. So we could just add that vector out on the end and say that's 80. Okay. We want to find out how many degrees off course will the plane end up flying, and what's the plane's speed relative to the ground. All right, speed is just going to be the length of this resulting vector. All right, the length of that resulting vector, let's pretend those two hit each other, and the degrees off course is going to be the measure of this little angle here. Okay, so does it make sense that that resulting vector is going to be a little faster? Yes, when we're on a plane and the wind is behind us, they call it a tailwind. It makes the plane fly a little bit faster, actually. All right, so how can we do this? Well, let's add these vectors in their component form, and that'll give us this new speed, right? So the component form for that first vector is easy. We'll call him vector 1. We'll call this guy up here vector 2. So vector 1 in its component form, it has no horizontal, only a vertical, which is positive 600. Because again, we're doing this north, south, east, and west. All right. Now, vector 2 would be a little bit different. I got to figure out what that angle is, right? If I draw a horizontal here, I need to find that angle there, and that will enable me to find the components here. I can do that, or, no, that's probably the easiest thing to do. All right, so we are flying southwest. This is a 45-degree angle, right? So we've got that angle measure. Now to find the components, well, x is simply going to be our cosine theta, and y is our sine theta. Nice and easy, okay? So r, that's the hypotenuse or the radius here. So that's going to be 80 times the cosine of 45 degrees, and y is going to be 80 times the sine of 45 degrees. And in this case, they're going to be the same, right? Because we know that the cosine of 45 degrees, we just looked that up, it's the square root 2 over 2, right? So this is going to be 80 times the square root of 2 over 2, which will simplify to 40 times the square root of 2. And Yep, we're up here in quadrant 1, so we don't need to worry about signs or anything, right? All right, so my components for vector 2 then in component form, it's going to be 40 times the square root of 2 for the horizontal and 40 times the square root of 2 for the vertical. All right, so adding them together, okay, will give me the component form of this resulting vector. We'll call him vector 3. Okay, so that's going to be, we'll add the, we'll call him vector 3. So we'll add the components, we'll add the horizontal components. So 0 plus 40 square roots of 2 is 40 square roots of 2 for the horizontal. Now for the vertical, that's going to be 600 plus 40 square roots of 2. All right, so that's the component form. Now to find the magnitude of V3, right, to find the magnitude, we just take the square root of the sum of the squares of those, right? The square root of 40 square roots of 2 squared plus 600 plus 40 square roots of 2 squared. Let's see if I can type this in the calculator. All right. All right, we want the square root of, yeah, we have a square root there. All right, so it's 40 square roots of 2 squared. All right, so let's put that in parentheses. 40 square roots of 2. Okay, we'll get out from under that radical. Close that parenthesis, square it. All right, there's that first part. Now I want to add to that 600 plus 40 square roots of 2. Get out from under that radical. There we go. Oh, I didn't want to do that. Let's go back and get that one gone. So get out from that radical first, then close off the parenthesis and square it. There we go. I think I got that one typed in properly, and let's see what it is. 659 point. I mean, I'm not even going to count that decimal. It's just not enough. All right. So what did we just find? We just found out the plane speed relative to the ground, 659 kilometers per hour. How many degrees off course? All right, we need to find the measure of this angle here, theta. All right, to find out how many degrees off course. If I draw that properly, I think I did. Okay, so I know the if I consider, let's consider this little triangle here. Okay, here's one way to do this with multiple ways. I know that one side is 600. Since I know the horizontal component of that top little triangle, I know this other side here is 40 square roots of 2. All right, so since I know of this triangle, I know hypotenuse, opposite side. I can use the sine. I can say that the sine of theta is the opposite side, 40 square roots of 2 over, oh wait, that's not the hypotenuse. Sorry, that's the other leg of the triangle. That's the other leg. So we have a leg and a leg. So we're going to use tangent, right? So we can say the tangent of theta is the opposite over adjacent. So that'd be 40 square roots of 2 over 600. So theta then is the inverse tangent of 40 square roots of 2 over 600. Okay, let's see what that is. Inverse tangent of 40 square roots of 2. Didn't get out from under the radical. Let's try that again, get out from under the radical, then close that parenthesis. Okay, 40 squared root of 2 divided by 600. And it looks like we're 0.3860 degrees. And what direction are we here? East of north. Whew. Okay, and that ends the lecture for section 8.4, vectors.